Hello everyone and welcome to today's Austmine webinar. I'm Sean Rooney, I'm the Membership Manager of Victoria and Tasmania. I'm here at Austmine and I'm pleased to be your host today. I'd like to acknowledge the traditional custodians of the various lands on which you all work today and the Aboriginal and Torres Strait Islander people attending in this webinar. For today's webinar, I'm joined by Ben Lewis, the National Business Development Manager for Mining and Water at Geofabrics, for a discussion on geosynthetics and risk mitigation in tailings. Ben Lewis is the National Business Development Manager for Mining and Water. He holds a Bachelor of Civil and Structural Engineering degree from the University of Adelaide and began his career as a civil and geotechnical engineer before joining Geofabrics, Australasia. In 2016 is when he joined. Ben has 7+ years experience working in the geosynthetic industry with extensive knowledge on selecting appropriate materials in contaminant and containment applications. Over the years, Ben has been involved in a number of high-profile mining projects, including the West Wallsend coal mine in New South Wales and the MMG zinc mine in Tasmania. For those that don't know, Geofabrics is in the business of geosynthetic engineering and building key infrastructure across Australia for over 40 years. They are focused on developing new and innovative products and providing customers with the world's best solutions to complete civil and mining projects. Their focus is to protect, contain and secure the physical environment using smart geotextile and geosynthetic products. So before we begin this, let's not underestimate the challenge tailings management is, and it's a global issue, and Ben will shine a light on the role of geosynthetics in it. Following Ben's presentation, there will be an opportunity for audience Q&As. You can use the Q&A button at the bottom of the screen to send through your questions at any time. You can also upvote on other audience questions that you most want answered. So without further ado, I'd like to hand over to Ben to begin the presentation. Welcome, Ben.
Thanks, Sean. Appreciate that. And thanks to Austmine for organising the event. Generally really good turnout, so much appreciated. So yeah, today I'll be presenting on geosynthetics and how it relates to risk mitigation and management in tailings. But first, I'll just give you a bit of an introduction. You've probably got a bit out of that from Sean, but Geofabrics, we are the sole geotextile manufacturer in Australia. We've got manufacturing arms in Albury and Queensland, where we produce geotextiles, GCL, which is geosynthetic clay liners, and we've got branches spotted around Australia at the main capital city. So we've got sales teams literally spotted all around, including Darwin. I think you've covered off on the bulk of what needs to be said about that, but we do focus on sustainable products, and I will touch on that a bit later. In terms of relating that to geofabrics and geosynthetics and our objectives in the mining industry, the main focus is really to protect the environment long term, provide a range of solutions, and what that really means is we want to be credible with the advice that we're giving. So we don't just focus on a single range of solutions. So we talk about HDPE, GCLs, BGM, LLDPE. We'll try and ensure that we're giving the right advice that we see for the right application, rather than just having one product to suit everything. And to follow on from that, we really do also try and push for site-specific and effective containment. So that involves potentially testing materials and looking at how these materials specifically perform in the site conditions. So it could be immersion testing, friction analysis, all sorts of testing that we can do within our grid laboratory, which I'll introduce in a minute. In terms of innovating and producing sustainable materials, what that really means for us is producing materials that will last the life of an asset. So in terms of tailings dams, ensuring that it's going to literally last for as long as it's needed to, but also producing materials that are out of sustainable materials. So we try and produce geotextiles, for example, out of recycled content where we can. And that basically takes recycled polyester from Coke bottles that were destined for landfill. So that's just one example of what sustainable means to us. And we're also trying to innovate constantly, trying to produce new materials that are suited to this industry. I suppose tying that back to GISTM, and I'll touch on GISTM in a second, but we do aim to adhere to GISTM as much as we can, and that really involves understanding what are the best practice environmental management means for the lining and containment. I mentioned the grid before, which is our geosynthetic research, innovation and development lab on the Gold Coast. We do a whole range of materials testing with HDPE, GCLs, geotextiles, drainage materials. But when it comes to HDPE, we can do pot immersions, which is effectively immersing these materials in Site 1 liquor or synthesized liquor to match what happens on site. And then you predict the lifetime from understanding the degradation rate of that material. That tends to take 6 to 12 months normally. There are new methods to accelerate that testing, and it really just involves thinning down the membrane to about 0.3 of a mil, and that accelerates that degradation process to 2 to 4 weeks generally. I mean, it would typically be a screening test to compare materials and how they compare against each other in terms of their performance, but there are new techniques and they're developing, and they could be quite useful for using up the front of a tailings or a project with a bit of risk involved. We do a lot of GCL, geotextile testing, which is thermal stability testing, UV exposure evaluations, interface shear testing to understand how these products interact with embankments on steep slopes, filter clogging testing. We look at cushion analysis for our geotextiles to understand and optimize what kind of geotextile we might need to protect a membrane from quite a coarse subgrade, like a waste rock, for example. So we can do all that in the lab to really optimize the solution for the site conditions. You do need to do this type of stuff up front of the project. So typically we need to be within a specification, or we need to be engaged by an asset owner. But it does really allow you, just aside from optimizing materials, it does allow you to validate warranties, particularly with the primary liner, which is generally exposed to the harshest conditions, and allow you to predict longevity, which is pretty important in these really long, 500, 1,000 year life assets in some cases. And as I said, we're aiming to refine the thickness of these materials, resin packages, which may be going into it, GCL grades, geotextile grades, resulting in a more cost-effective design, but also instills confidence in maybe the investors, the insurers, which are a big part of these mine sites. So really the aim is to mitigate risk and ensuring optimal performance over the asset's life cycle. So when it comes to GISTM, I won't tell you how to suck eggs because I'm sure all of you are pretty familiar with this, but it was developed by the UN, the PRI and the ICMM back in August 2020. And it was really designed to, it was the first global standard really for the mining sector and set a benchmark for tailings dam safety, with the aim of really creating zero harm for the people within the mine site, surrounding the mine site and the surrounding environment. Really, and aiming to prevent catastrophic failures, which were and still are occurring, and they're quite prevalent, really. And so the aim is to prevent that happening. And it was a step change in providing transparency with what happens on these sites and being accountable to safeguarding the people. It does mention the word risk 70 times. I went through it, did a bit of a analysis. So it is really pure and simply about risk mitigation. And the engineer of record, along with geosynthetics, I think play some of the most significant roles in that. The role of the engineer of record, I'll just summarize that quickly. There may be some engineer of records listening in, but effectively their role is to foster transparency, accountability and community well-being, implement best available technologies, and that would include geosynthetics and other monitoring devices. But in short, these engineer of records have a huge responsibility on their shoulders. So they have to look at and combine a lot of data. And I think robust lining systems using geosynthetics enable and basically decrease the risk of these engineers dramatically. So relating geosynthetics to GISTM, there's these 5 statements within that than the GISTM, I think, translate quite well and help me understand how the relationship works. But preventing catastrophes, risk mitigation, transparency and accountability, safeguarding rights, and best technologies adoption. So what are we doing with geosynthetics? We're effectively trying to, well, if it comes to lining systems, that is, we're effectively trying to avert leakage and maintain the structural integrity of the embankments, which are really the biggest risk in terms of catastrophic failures. And traditionally, a lot of these dams were unlined and they were designed to leak, and that was fine back in the day, and sometimes is okay these days, but it's really assessed on a case-by-case basis. What geosynthetics also allow in terms of accountability, they offer measurable solutions. So depending on what your liner profile can look like, you can have a double liner system with a drainage layer in between, and you can actually quantify how the primary liner is performing in terms of its leak rate. And you can assess that back against the warranty if you've done testing. And it also allows your engineer of record to assess and monitor the system a lot better. They also geosynthetics allow to minimise impacts to the communities and the surrounding ecosystem. So it all ties quite well in with each other. And in terms of best technologies adoption, many suppliers, the good suppliers will try and innovate and develop their materials for site conditions. So we're always trying to come up with either new solutions or tweaking existing products to improve how these things work on site. So just going to the consequence of introducing lining systems, there are negatives and positives, obviously. It's not all good. Effectively, by introducing liners, we are effectively going to increase storage capacity because we're not going to get as much leakage through the asset generally. So by retaining more liquor or water, the dam will fill quicker. Now, that depends on what type of drainage systems you might include within the dam, but that means you do have to include drainage internally. Liquefaction risk, again, if you're not including drainage within that lining system, you can increase your risk of unstable tailings in some ways. Obviously, you're protecting the embankment from saturation, but you're retaining that water on the inside. So really, maybe, again, it depends on the site. Maybe there's a rate of filling within the tailings dam, which means that water is being evaporated off. So it maintains a good stable nature, but quite often that is difficult to do. So including drainage is quite important. Additional cost, obviously, that is the biggest one and one everyone wants to avoid. So that is a factor. Potential for leaks. All materials have their risks associated with them. HDPE has stress cracking risk depending on the formulations. BGMs have certain risks, and I'll go through all this in a minute. And GCLs obviously have their other risks as well. So I'll touch on those. But the positives with introducing lining systems, we're preventing leaks, which is generally always good. If it may be inert, it may be contaminated. Obviously, we're going to protect the embankments for stability. We'll enhance the stability of the tailings if you're reducing the risk of liquefaction through drainage. Better public perception. I've touched on that already, but that is a big one, I think, really appeasing the surrounding view of how these mines operate. So public perception can be critical, but that can also lead to better insurance, lower insurance cost, and more investment interest. So I think it's only about 30% of the mines around the world have adopted the GISTM guidelines, but I feel a lot of the insurance and investors are pushing for this more than anyone. You've got the regulators, but you've got the insurers and the investors probably pushing for GISTM compliance because that's what they want to see, and that probably comes from better public perception, but also just obviously environmental benefits. Enhanced water recovery. If you're introducing drainage materials within the dam, you can actually get better water recoveries as well. In some cases, for a tailings facility, I'd heard from the site that they were getting about 10% better water by introducing a geocomposite above the liner than they would have just relying on a typical decant tower. Criteria for, I hope the noise in the background, guys, isn't putting you off, putting me off a bit, but criteria for material selection, in tailings. So the GISTM advocates for transparent material selection. So what we and the consultants and the regulators should be endorsing or encouraging is assessing design life expectancy. So how long is this asset required to perform for? Subgrade type, what does the subgrade look like? Is it rock? Is it clay? Obviously, liners prefer a smoother surface because it's better for stress. But if it's rock, what do we need to do to assist with that? Chemistry of the liquor above or below the liner, how's that going to interact with your lining system? UV exposure and climate. Is it going to be hot? How much UV is it going to get? What's the impact of the thermal exposure? I mean, tailings dams, their rate of filling and covering can change dramatically. So you do need to assess how quickly they can be covered. Temperature of liquor, obviously, that accelerates the degradation process of lining systems. Slope of embankments, I understand that most tailings facilities want to have steeper embankments because it means less civil works and less footprint used. So a lot of people want to go as steep as possible, and that's great, but that does have an impact on what material you would use. And you would have to look at the friction capacity of that membrane. But again, there's options for that, and I'll touch on those. And allowable leak rates. So this all ties back in with really the GISTM advocating for transparent material. Allowable leak rates, particularly, is one that can be, I suppose, measured through using geocomposites as well. And in terms of what are the common materials, I've mentioned a few of them already. I think the most common we see, outside of there being no liner and relying on either just a filter, is HDPE geomembranes, which are high-density polyethylene, effectively unreinforced plastic, but with the ability to formulate with certain additives and resins for the site conditions. There's LLDPE, which is linear low-density polyethylene, which is a bit more flexible, but with probably less chemical resistance than HDPE. You've got BGMs, which are geomembranes made from polymer-modified elastomeric bitumen, and that is a reinforced product with a polyester reinforcement. And then you've got GCLs as well. I think they're the four main lining systems I'd suggest that have been used in tailings in Australia, at least. And GCLs, by the way, are, if not familiar, are bentonite clay sandwiched between geotextiles needled together, and they do require confinement soils on top permanently. And then you've got a whole range of other systems like geocomposites, which are drainage nets or strip drains. You've got cushion protection geotextiles, and you've got conductive layers. So conductive layers I haven't mentioned, but they are basically conductive geotextiles or a conductive medium which goes below a particular liner, typically the primary main liner, and it allows you to spark test and run a current through the conductive layer, spark test the primary liner, and you basically have someone walking across that completes the circuit with a broom that's connected to that conductive medium, and you get sparks jumping through any holes. So it's a way to CQA test your primary liner for holes, and it really dramatically improves your system because you'll go back and patch those holes and end up with something that's far less leaky. So I'll just now touch on the drawbacks and benefits of some of these materials. So I'll start with HDPE. Number of positives. I mean, HDPE is relatively inexpensive compared to all the other materials on the market. I'd suggest it's the most inexpensive or the least expensive. It's relatively quick to install. That comes from the wide rolls, 7.5 to 8 meter wide, and it's quite lightweight comparatively to others. Excellent resistance to chemistry, and the ability to formulate these materials is really important when we're dealing with harsh chemistries and long-term exposure in maybe harsh climates. So it is important to know that HDPEs are not all the same. They can be formulated, and you look at a data sheet, it still won't tell you the full story, and that's why we really endorse testing materials. UV resistance is a pro generally with HDPE, depending on the product. Color customization, we can also add colours to the top of it, and that basically means if you added a white coating to the HDPE, you can prevent a lot of the heat absorption, which causes the wrinkles with polyethylene liners. So if you can reduce the wrinkling, you can get far better performance in terms of potential leak rates. You get better intimate contact with the subgrade. It's far easier to work on and install because it doesn't get as hot. I mean, a 30-degree day on a black liner, whether it's HDPE or BGM, will get to about 75 to 85 degrees C. You can imagine working at those temps can be quite challenging. Whereas if you make it white, it will reduce it to more like 50. And the thicker the coating, we tend to find, and we're doing a bit of work with this at the moment, is the thicker the white coating that goes with it, the better the thermal benefits. And you obviously get less aging as a result when it's exposed to the sun. Textured options as well with HDPE, you'll get increased friction on slopes, as I said, and it actually reduces wrinkles, oddly enough. But there's been a lot of work done on that. But with texturing, there are different available options again. There's different asperity heights, there's different spacings of these asperity height, and there's different sort of texturing. So you've got embossed texturing and you've got a spray-on types. And they perform quite differently in terms of what friction angle you could achieve on a certain subgrade. But you tend to achieve at the high end of about 30 degrees with complete intimate contact, so it's sitting flush. But that is the target with the high-end friction HDPE. And then you've also got this industry standard GRI GM13, which many may be familiar with, but that is, and while it's a great benchmark, it's more suited to lower risk and short-term storages. I mean, there's a thought that it's a 10-year limit to that standard. And I think I still see a lot of specifications in the tailings sector relying on that. And I think it's probably a little bit outdated. It was updated, I know that, to increase some of the performance criteria, but there's still a lot of reasons that you would do either site-specific testing or increase some of those parameters yourself based on site conditions. Cons, negatives, HDPE, poor flexibility, can't be prefabricated. It does have a susceptible nature to stress cracking, but as I said, you can add formulations to mitigate that by introducing different resins and better manufacturing technique, and that can dramatically change, for example, stress crack resistance from 500 hours on a data sheet to 5,000 hours. Wrinkling, no one really likes the fact that HDPE wrinkles. As I said, you can limit it with adding white to it, but otherwise you just need quality installers to manage that. It can be a bit of a pain, but that's why there are installers that do this every day. Need for protection geotextiles. Yes, you can in some cases need geotextiles to mitigate stress cracking risk or puncture from subgrade, but it's the same for any membrane. I know that there's a theory that BGMs do not require protection geotextiles, but I would suggest it's great. BGMs are great for installation damage benefits, but in terms of long-term performance, they still have certain consideration. I'll touch on that in a minute again. Installation expertise, yes, you do need experienced installers, so that does add another cost, and they have to weld the product together, and you want quality CQA, because with a lack of CQA, not as much care gets taken with these installations. So you want quality CQA, which is construction quality checks. Common misconceptions I'd suggest are unsuitable for steep slopes. Proven to be effective, they are actually proven to be effective on 1 to 2 slopes with certain textures. So I wouldn't count it out. Uniformity of HDPE, not all HDPEs are the same. There are formulations and antioxidant packages which vary between the suppliers. And so you can actually make a product to suit a certain liquor. But obviously you have to have a data sheet as a benchmark. And that's why a lot of people just tend to want to rely on data sheets for certain projects. But for tailings and contaminated liquors, you'd want to be talking with suppliers about, what options do we have, and susceptible to damage. I've touched on that. In terms of the texturing, you can see that's what it can look like, the different embossed texturings. It's quite obvious. There are different types. There's also blown film, which is a very rough finish, and that could be rubbed off. So there are certain texturings which work better. The additive packages, you can see that's just an example of what gets added in as the antioxidants. And then the white, that's typically what a white, almost a full white HDPE would look like. And we can make all sorts of colors. And so moving on from HDPE, benefits and drawbacks of BGM. Sorry, I should have changed that title there. But this is BGM, bituminous geomembranes. Yes, pros, they're very robust and great for damage during installation. And I'd suggest exposure to wildlife damage long-term, if it is going to be exposed long-term. Maybe not for a tailings dam, it's going to be buried eventually. Relatively heavy, so it goes down relatively easy, but in terms of installation limits, there is still a pretty similar wind speed limitation when it comes to installing, and that's not necessarily the weight of the material. If I compare BGM to HDPE, the BGM, and I'll mention this in a sec, has a pretty agricultural method for welding, and while it's easy, it is an open flame technique. So if you've got windy conditions, you'd want to avoid installing BGM because that flame can flick around a bit. So while it's heavy and it makes that an easy installation to go down, you do need to consider the other things about the flame welding. Good UV resistance, and it's long-term proven UV. It's got a long history in roofing applications, which is what it was developed for 40 years ago. Well, it's probably got a longer history actually, BGM, but in roofing. So Terranap or Ciplast, our supplier, has been around for 40 years. So they do have a long history, but less so in maybe tailings. And it sits flush. Now that chart on the right doesn't apply to any of those comments on the left, but I will mention it. What it does talk about is how BGM basically changes properties with heat, which is certainly a consideration. Basically, what this chart shows, if you can see my mouse, maybe you can't, but the top line is an indication of a friction performance at 20 degrees Celsius, and the bottom line, that red line, is an indication of friction performance at 60 degrees C. So we've effectively got a loss, or a reduction of 42 degrees peak friction of BGM on a particular slope, 42, that's an angle 42 degrees, compared to 18 degrees of an angle once we add about 40 degrees Celsius more heat. So effectively we're saying you get about over a 50% reduction in friction performance when you introduce heat. And that heat could come from waste rock within a cap, it could come from the sun. So they are factors which really should be considered in design rather than relying straight on lab factors which are done at 20 degrees Celsius. Drawbacks, touched on that one already. Questionable compatibility. I think there's been a bit of limited work with chemical compatibility with BGM, so I just suggest doing testing and take careful consideration. There are only 2 products on the market, and they don't have the ability to formulate for site conditions at this point. So if you've got any concerns, you probably want to assess how it interacts with chemistry. It still is susceptible to aging and brittle cracking. It's not called stress cracking. I'd suggest it's called aging cracking. So it will age and oxidize and it will crack eventually. So it's a similar scenario to HDPE in that respect, but it is reinforced. No formulations, as I said, elongates and softens with natural heat, which I indicated with that friction chart before. So that is a concern maybe if you've got really steep slopes and you're changing the friction performance due to heat, and then it starts to soften and it can elongate, and you can get slumping at the bottom of slopes if they're too steep. And the other thing is be wary of exposing welds long term, because, and I'll show this later on, there is some evidence to suggest that welds can drop by the strength of welds in hot conditions. I'm talking greater than 30 degrees C. You will get a loss of about 80% in the weld strength. So something you can either factor in but you can imagine if you're on a steep slope, again, you get slumping and you had a weakened weld, you just have welds separating, and we have seen it. Even though CQA might have found that a weld might have passed initially because it was done at a cooler temperature. And limited construction quality at this point in time. I mean, there will be developments, I'm sure, for improving CQA, but HDPE tends to have a lot tighter CQA requirements. Incompatible with geocomposite drains. I wouldn't be using BGM over a drain purely for the fact we've seen and heard it melting into the drain when it gets hot. Time-consuming installations in comparison, and welding requires experienced installers. That's the same as HDPE. Proper welding of BGM requires skilled professionals. Otherwise, you will get issues with welds and consistency. So, in terms of common misconceptions, I'd suggest one of those is BGM does not need ballast. In some cases, you might get away without ballast. If you're sufficiently anchoring the product at the top and bottom of the slope, the ballast is only, and the anchoring is really only needed to resist wind uplift and suction, because you're going to have permanent tailings ballasting over the top. But that does need assessment. I've seen jobs which still require ballast, particularly in the basal areas, but where you typically wouldn't anchor it very quickly. Depends how fast you're going to fill these storages. Superior frictional performance on slopes. I think the book values suggest, yes, it does have a superior friction to others, but it does change in terms of its performance, like I've shown. So just be wary of how it's going to change. Deployment over coarse rock. BGM should be treated pretty similar to any geomembrane. The cost benefits of installation and ease as well. So it does prove to be a more expensive option, but you have to consider what else goes with these solutions. Maybe HDPE requires a cushion and a drainage. Maybe other systems don't. And just finishing up with BGMs, you can see what the actual picture of a cross-sectional close-up view of the material looks like. It's effectively a sanded surface with a polymer SBS modified bitumen core, and then the reinforcement, the polyester reinforcement, and then a polyester film on the underside, which is quite slippery in some cases. Now, this particular photo here is some recent testing we've done. It's called a compound stability test, basically assessing how it performs. And the reason we did this was to understand how BGMs perform on slopes, because we were seeing a bit of slumping in some cases. So we wanted to understand what actually happens as we increase the temperature in these vertical, almost vertically held compound stability tests. So we raised the temperature. I mean, that's 130 C. That's rarely going to happen. But we did see a lot of changes from about 80 to 90 C. So it just shows how this material can start to shift under heat. Benefits and drawbacks of GCLs. Pros, comparable to HDPE in terms of its cost, I'd suggest, and that really comes down to the fact there's no welding. And that's not factoring in the confinement soil required on top, which can be expensive depending where you're sourcing that confinement soil from. Ease of installation, no welding, as I said, reasonably rapid, resulting from no welding required. Robust construction does have inherent cushioning properties. So, and that next point there about demonstrating self-healing properties up to defects of 40 mil, and I'll demonstrate that later in a paper. But you basically, if you end up puncturing a GCL during an installation and you end up hydrating after it's in situ and rolled out, those holes up to about 30 to 40 mil completely seal up, because that's the way that bentonite works. It effectively swells to a lot larger than its initial state. So it has the ability to swell, and that depends on the chemistry of the liquor as well. And a calcium carbonate solution, like a calcium type cover soil or an acidic material, can limit the swelling nature of it. So, but it just goes to show that it allows you to be a bit less careful with the install in terms of damage and puncture. Cons, limited applicability. It's not recommended as a primary liner for deep hydraulic ponds, so that's not really related to tailings, but it's worth noting. Confinement soil requirement, it requires 300 mil, as I said, over the top. You do need to check for near stability. Obviously, the steeper we go with a GCL on a certain embankment, that 300 mil veneer stability has to be checked, and there are limits to slopes. So if you really want to go a long slope on a GCL liner, then you have to increase the thickness to reduce the slope internally. Otherwise, you will get basically eroding and slumping of that cover soil. So that's something to factor in. Bentonite moisture sensitivity. It shouldn't be excessively saturated before covering, but we know, and I've mentioned this over here, that it can sometimes be hydrated, and some are okay at 100% moisture, noting that these products go up to about 300% moisture by weight. But at 100% moisture, we've checked and seen that ours is okay, and the risk really is, once you get it to that saturation point, you can risk overswelling and it basically coming out of the product before it's covered. So you want to avoid that and maintain it in a pretty much dry state until it's covered with those initial 300 mil of confinement soils. And again, GCLs, just like any other membrane, they all do not perform the same. And looking at a data sheet, you might see it looks identical, but in actual fact, they can perform very differently in the different chemistries. So testing is encouraged. Photo on the left there is a powdered bentonite. That middle one there is a granular bentonite. There's not too many granular bentonites around, but you do come across them. You can imagine a powdered bentonite is going to have a far better impermeable properties than a granular bentonite. That's something that you won't see on a data sheet, so something to be aware of. And then in terms of what I was talking about before and swelling ability of the bentonite, I'll go to the next page. So this top chart looks at the impacts of deionized water, which is ideal for saturating bentonite, compared to the bottom chart, which shows you a calcium carbonate solution. And basically, looking at this top table, what you can see here is that basically they pushed an initial hole in the GCL, they saturated it, and then they assessed what that hole looked like afterwards. So the initial hole, 34 or 34.9 mil, it basically shrunk to zero. A 50 mil hole hydrated with a deionized water still shrunk to zero. So you can see it is quite effective at swelling around these size holes. But when you start to introduce chemistry, there is a massive reduction or a massive change. So you can see here, the 41.3 mil hole still had a 26 mil hole after hydration. So this is why we test. It changes the swelling nature of it, and it changes the permeability of bentonite GCLs. In terms of common liner profiles and tailings and selection factors, so no liner would be preferable for cost purposes, obviously. It does introduce instability risk depending on the nature of the tailings. It's not suitable for contaminated waste, I'd suggest, or high rainfall areas where you're going to get constant saturation of the tailings. I think a combination of those as well would be not appropriate. Single liner would be the next step up from there. HDPE, BGM, or GCL, suitable for inert tailings, I'd suggest, or scenarios with relatively dry contaminated tailings, and appropriate where low hydraulic heads and high evaporation rates are expected, which low hydraulic heads would be most tailings facilities, I assume, because tailings tends to be quite self-impermeable. So therefore you have these sort of layers of the hydraulic or phreatic zones. Compare that to a water storage, which is just purely water. But high evaporation rates also help with the stability of the tailings and I suppose the impact on the liner. Double liners, which is effectively an HDPE with a geocomposite net with another layer of HDPE. You tend not to be using GCL or BGMs in these type applications because as I said, you risk the BGM maybe melting into the net if it's exposed, or GCL potentially swelling into that net. These can be tested though, so it could be done potentially. But it's typically double liners are used to understand asset performance and really leak rates. So you would introduce it to be able to quantify how your asset and your liner is performing. So it helps the engineer of record to literally assess how their asset is going. And it also helps with the proving up of warranties. Double composite liners are very rare. It's effectively adding another GCL layer below a double liner. I would say it's quite rare unless you've got highly contaminated soils, you've got a site which is being looked at very closely by regulators and by investors, insurers, and all that. And in that case, that would drive that kind of design. So really, decision factors to weigh all those up are public perception, cost, investor confidence, insurance risk, other environmental factors, and climate. And when it comes to common construction issues with lining systems, we've got whales occurring, so they call them whales, which are essentially floating liners, and they occur when you get air trapped under the liner, where you might have a leaking liner as well. You've got water building up underneath, and you've got a combination of wrinkles and air trapped. And as the and this is more applicable, by the way, for water storages, but it can still happen in tailings, more so before the tailings has been deposited. It's because tailings are heavier than water, so you'd likely compress the liner down, and it would basically compress the wrinkles. Not ideal, because compressing wrinkles could cause stress cracking over time, so you want to avoid this happening in the first place. And the way you do that, and I'll touch on that later, but there are 2 methods for doing that. I think that's all I'll say on that. But you can see it can get quite dramatic. But it's good to know there's ways around it. That's what I was going to say. The way this can occur in tailings is when you might have a black liner on a subgrade, whether it's HDPE, BGM, and the evaporation caused by the thermal gradient directly onto your subgrade from the black liner can cause quite a lot of evaporation on your subgrade, and can cause basically a build-up of water immediately under your liner. So again, there's ways to drain that, and I'll touch on those. Bulging liners, trapped gas occurring. So basically, if you've got a wrinkling liner on a subgrade and you don't drain it using you don't get rid of the air that's trapped underneath, and you start to fill a liner, whether it's a tailings facility or a water storage, you can get this air trapped, and it can, if there's no way to vent it through either strip drains, is pretty typical, like shown in that bottom photo. You tend to, I think that's a pretty bad case on the top photo, where you get this massive amount of air trapped under the at the top of the crest. So there's, again, simple ways to avoid that in design, and that's through venting and releasing air at the crest of the trench. Wind uplift. There are ways to resist wind uplift by introducing ballast or sufficiently anchoring at the top and the bottom of the slope. And there's design practices for that, and the consultants are generally all over that, but it is a factor to consider. And generally, the deeper, the stronger the wind, the larger the slope, the more likely the membrane is going to be sucked off the slope. Therefore, you might have to deepen the anchor trenches. Wrinkles. I'll speed along here. There's not much to go. Common construction issues with lining. This really just shows the difference in what a white liner on that far right, bottom right photo, compared to a black HDPE, you get far less wrinkles. So that's just a visual of what kind of benefit you can get from using a white membrane, HDPE that is. Installation damage. Obviously, you will need to be careful with any particular liner. Failing HDPE welds and CQA, that can come down to both poor welding technique, but also poor product. So you've got standard oxidization induction time, which is a performance criteria for HDPE. The lower that value, the more problems you're likely to have with welding and CQA. But introducing CQA at least allows you to find those issues. Slope too steep. I'll push on here a bit. I think I'm at the end anyway. Common construction issues. I touched on this one earlier. The tensile capacity of the welded BGM tends to drop in the heat. So that bottom chart, this was taken from a Golden case study where they assessed temperature at 27 degrees and temperature of the weld at 66 degrees, for example, and it went from 12.2 tensile strength, kilonewtons per meter, to 4.7. Keeping in mind that all this material was CQA checked and tested, and this was a few months after the installation. So everything was signed off. And in this particular job, they had to pull it out and replace with different material. So I might leave it there. I've got a few other things to say, but I suppose just this last slide. Consider drainage below liners, venting, using light-coloured membranes if you can, using 1.5 mil HDPE or thicker if you are going to use HDPE. The reason for that is you get immediately better durability in terms of chemical compatibility, but you also get better weld performance because of maintained stabilizers under, because obviously a lot of heat goes into that weld during that welding process, so a thicker material can resist it and last longer. I would suggest avoid BGM on really steep slopes. Spark testing primary liners if that's feasible. That does add cost, but it does improve CQA dramatically. And that's it. Thanks, guys. Appreciate listening. There's a few comments there if you want to have a look at them, but happy to share the slideshow with anyone and take any questions if there are any.
Fantastic. Excellent presentation. Thanks very much for that, Ben. And I wished I'd actually seen your presentation when I was doing lots of rehabilitation work in the mid to late 90s in north east Victoria, because we certainly had a lot of failures in terms of the tailings dam and liners. So so now it's time for questions, if we have any, from the audience. And please use that Q&A button on the bottom of your Zoom presentation and forward any questions. There was one question there that's come through from M. Galbraith. And so the question is, if a liner was sufficiently hydrated with DI water after installation, but then exposed to water of varied chemistry, would it retain its DI water healing ability?
Look, we've actually looked at that for a few jobs. So we do suggest pre-hydrating GCLs in some scenarios with DI water for that purpose. Say it was a pavement it was a fuel bund or something, and the GCL was going under a fuel bund pavement, and we didn't want the potential spill of the fuel to impact the GCL because we knew that it has a negative effect on the bentonite performance. Then we actually pre-hydrate, and that ensures that and as long as it's maintained moisture as well. So if you've got the cover soils there, you've got a concrete pavement over the top, we can maintain the moisture in that. Then yes, effectively like a diesel would not mix in with the bentonite. So there's ways to do it. It wouldn't always work, but we'd have to assess it case by case.
Okay, we have another question here. With the cracking due to age in BGM, will it affect the permeability?
Well, it depends how deep the cracking goes. I mean, and that depends on the conditions in the climate. It would eventually, for sure, because if the cracks can reach the reinforcement, and then the reinforcement is degraded by the hydrolysis or by the chemistry, then that's your strength of the BGM gone, and then that would degrade, and then the cracks would continue to propagate through. I think that the case studies and the projects that I've witnessed in cooler climates where we do see some alligator cracking, we tend not to see too much further propagation because of the climates, but in Australia, that's certainly a consideration. Yeah.
Okay. So there's another question here, but I might actually ask one for myself. How does the adherence to the GISTM and best practices impact the regulatory compliance?
Sure. Look, I'd say the regulators are trying to adapt and learn as much as designing consultants. So they're sort of working to GISTM and adapting as they go. They've got to appease all parties. They've got to consider environment, costs, engineering, design, and time to approve. So everyone wants to see these assets these new designs get approved as quickly as possible. And GISTM may improve or make it slower. I don't know at this point. But I suppose adhering to GISTM and the best practices can lead or should lead to time saved. If there's a consistent approach and it's the best practice method, it should be a faster approach, but also lead to less environmental impact. But on the flip side of that, it can lead to higher CapEx costs.
Okay, thanks for that. So there's a couple of questions here, and they all relate to BGMs, but also the steep slope. So I'll try and combine the questions. So what would be a steep slope gradient for BGM liners?
Again, it depends on the subgrade. Clays are a bit slipperier. So if you've got a clay subgrade, it might be 1 in 3, 1 in 3.5. For coarse material, it might be 1 in 3. I'm hesitant to maybe 1 in 2.5. I'm hesitant to push it steeper than that, just for what we know for exposed BGM on slopes and maybe worlds opening up when you do push it too steep. So I think it's, again, I'm sort of stating some ambiguous numbers, but the best way to do it is to do the testing up front, and we can help with that. It's a pretty quick test. Literally, if we get a sample of material from site, we understand what slopes you're proposing, what load, we can do a test within a couple of days. We get the sample of rock, or we can pull data out from what we've got already and try and match it up with site conditions.
Okay. Another question here has come through. Can you elaborate on the test method for determining the friction angle change with the temperature?
Look, it's probably one for the lab. That was done by our lab internally. There's been a lot of testing on this, not just within our lab, but globally at the moment, on understanding thermal impacts, particularly with BGMs. So I probably can't speak to that well enough. So you can follow up with me. You've got my email somewhere, and I can answer that through the lab.
Okay, thanks very much. So another question for me: how do you balance cost effectiveness with the need for durable and sustainable materials in tailings dams? Like, how do people go about that? Because obviously, you've mentioned cost is obviously the main issue most of the operations will be thinking about.
Yeah. Well, really, the key in that is to use sustainable and proven technologies. For one thing, if you're expecting 1,000 years out of an asset, spending time and money upfront with materials testing and proving it's going to work is worth it long term, irrespective. But having said that, a more expensive material isn't always going to be the better option either. So the idea is to prove and find and optimize what's going to work best.
Okay, thanks so much. So another one again from me. What emerging technologies or innovations do you foresee in tailings management and geosynthetics moving forward?
We've probably, well, I think I've been working on the geotube dewatering side of the business for a while, and the mining industry is taking a lot of interest. So geotube dewatering is basically geotextile tubes where you pump full of slurries, and it's a passive way to dry out waste slurry. And I see that as quite emerging. There's a few really interesting projects we're working on, which are taking the full tailings volume and almost replacing a traditional wet tailings storage facility. So it's kind of comparable to mechanical, but mechanical would be belt filter press systems, which are pressure based. Our geotubes are more passive and gravity dewatered. But there's some really interesting projects happening. I can see that as developing further. Yeah, I'll leave it at that one.
Okay, hang on, other questions just come through. What additives can be used on HDPE to minimise stress cracking, and what would this increase the cost heavily, or would it still be sort of roundabout within the same cost framework?
Sure. In terms of the names of the additives, I can't think of off the top of my head. There are a number of names, and they're quite technical, but that's for the technicians to work out for us. But in terms of costs, if you look at an HDPE product, it's 97% resin. It's roughly 2 to 3% carbon black, and it's got really 1% or less than is the added antioxidant packages. So it's very minimal, but they're very expensive. But getting that mix and blend is really important. And looking at the data sheets for HDPE, there are some performance criteria within that, and there's high pressure induction time, there's standard oxidation induction time. And when you look at the figures alongside those values, they can go up, but they're only measuring the volume of antioxidants. They're not telling you what's in there and is it appropriate for my, brine? Is it appropriate for my acid, alkaline solution? So yes, we use those as standard tools to tell us, it'll be a written spec by an engineer and we have to comply with that. But in reality, it may not be applicable. Now, coming back to the question about cost, it's probably 50 cents dearer, 50 cents to $1 worst case for a superior material. I mean, there's BEPM guidelines, the best practice environmental management guidelines, which was written around landfills, and that set another benchmark really for HDPE beyond GRI GM13, and that stipulates certain performance criteria as well. But having said that, setting benchmarks, and I don't know if I said this already, stifles innovation. So it just means everyone has to meet it, and no one's going to push for more unless there's a reason to do it. And if a industry like GISTM or a guideline like GISTM endorses innovation, then I think it's better for the industry.
So I'm afraid that's all the questions you have time for today. There's one more if you're very quick. Ben, if you can answer it really quick. How do you prove the expected life of the liner? Is it like a certified life? Who's the certification authority?
Yeah, well, the only way to really do it is we send the material to a lab with the liquor or the site one liquor or synthesized liquor. We immerse it, we accelerate the degradation process, and they extrapolate and do an Arrhenius modeling plot, and that is there to predict longevity. And you try and consider a whole range of things. It is quite hard to predict, but it's the best way to do it at this point. The problem is, as I said before, it does take a lot of time in traditional methods, 6 to 12 months. And this is for HDPE. For GCL, predicting lifetime is very difficult. For BGM, I don't think we're quite there yet either. But for HDPE, the technology is there, and so I don't know if I answered that properly, but it's really up to the lab to offer a report to produce that. And it's not just our lab; it could be an independent lab like XLPLAS or TRI, that type of lab.
Okay, so thanks very much for that. That's all the time we have, because I've only got like 2 or 3 minutes left. I'd also like to give a big thank you to everyone today for tuning in, but also especially to Ben Lewis and the team at Geofabrics for sharing their expertise today.